Now we could just check our work to make sure that if I take 25.53 times 1.12 plus 4.47 times negative 1.92, that I get about 20. And there's going to be some rounding error here because we rounded off these values, but it'll get us pretty close. So what we can do now is we can now write the equations for I of t and a of t, and we'll go ahead and do that next. Give ourselves a little more space here. So we know that from the diagonalization vector decomposition theorem that we can write x sub t in vector equation form by taking k1 lambda 1 to the t times v1 plus k2 lambda 2 to the t v2. And so we recall that xt just contains our infants at time t and our adults at time t. And k1 is 25.53. Lambda 1 is 1.79. And that's multiplied by v1, which is the vector 1.12 and 1. That's this guy here. Plus our k2, which is 4.47 times lambda 2 to the t, which is negative 1.04. So we got to be careful here. We'll write negative 1.04. That's all to the t power. We didn't really even need the parentheses here because this is a positive value, but here with this negative, we just want to make sure it's negative 1.04 to the t, because that's our value of lambda. v2 is the vector here, which is negative 1.921. And then when we do all sorts of multiplications here, we get that I sub t, is equal to, when we multiply 25.53 and 1.12, we get 28.59. And that's going to be times 1.79 to the t. Just for consistency, I'll put my t above the parenthesis there. And that's going to be minus, because I'll have 4.47 times negative 1.92, which is negative 8.58 times negative 1.04 to the t power. And a sub t, if I do the same thing, well, these just multiply ones. So I'll have 25.53 times 1.79 to the t. And this will be plus 4.47 times negative 1.04 to the t. So one thing that we should notice already is that as t approaches infinity, the term that has the largest base is going to be dominant. Right? Now, we're not saying that these terms go to 0, but negative 1.04t will be negligible in comparison to 1.79t to the t for very large powers. So we're going to say that this is negligible. We're going to say that this is also negligible. And so over time, we see that the populations are going to grow by a factor of 1.79. So there's going to be a 79% growth rate, and there's our dominant eigenvalue right there. So what's going to happen over time is this vector, this initial state vector, 2030, is going to point in the direction of the eigenvector 1.12, comma 1, and we can actually take a look at to see that this is going to be an exponentially growing function by producing graphs of I of t and a of t using appropriate technology. Now I've already got the graph here for the two populations. So down here you can see I have infants at time t and adults at time t, those equations that entered in. Just notice that I have negative 1.04 all to the power of x. And then here I produce tables, and I'll show you why I had to create tables in a second. But it has to do with taking a negative number and raising it to fractional powers. Because sometimes, like if this becomes x is 1/2, the square root of a negative number is undefined or is not real, and so we can't do it for really many of the non-integer powers. So as time progresses, we see that the infants are the green dots and the adults are the purple dots, and we can see that the adults are growing exponentially. The infant population is growing exponentially. And actually, we'll be able to see that the growth factor is about 1.79 or 179%. So we get all of the population from the previous time unit, but about 79% more. So let me come over to Desmos and just show you how this graph looks. Now, if I don't graph these and I put these equations in, we're not going to get a very pleasing result. Nothing gets graphed. I already know that my initial populations are 20 and 30, but I don't see anything down here. So the issue is the negative powers. That is, the negative bases raised to powers that are potentially fractions. So again, fractions can be square roots and stuff like that, and it's not always defined. So what I did here is I just put in a table, and once you have these two functions defined, I of x and a of x, here you can enter x values, and over in this column I will call this a of x1 because the values that I enter in this column will be my x1s. And then here I want I of, I guess we can do this in opposite order, I of x1 and a of x1. And now I'll start putting in some values here, and you'll see those points start to get generated as we move along. And oops, we'll take this guy out. And then 4 and 5 and 6. And so we can see that these populations are getting bigger and bigger. Now, one of the things that I want us to notice is that if you look at the growth rate from 535 to 929, that gap is getting much larger. And in fact, if I take if I compare, let me insert another expression here. If I compare I of, let's say, 15, and I divide it by I of 14, you can already see that 99,104 to grow to 177,438 represents a growth. It almost doubled. It was about 179% of its previous value. And also, if I look at a of 15 divided by I of 14, now that's not quite at the 179% yet, but if I start to make these bigger components in time, like I of 100 divided by I of 99, you can see there's our factor of 1.79, and if I do oh, you know what? I divided the wrong values here. This should have been a of 14, and it's there, 1.79. So the growth rate, that first term in these two expressions, is taking over rapidly. This second term rapidly becomes negligible. Now, if I compared and I should see that same thing here, if I compared the adult population at time 100 to time 99, I see a perfect 1.79 growth factor from time 99 to time 100. Also, if I look at the ratio of values for I of, say, 15 divided by a of 15, if I do I of 15 divided by a of 15, what I should notice is that ratio between those two values starts getting close to the ratio of I and a in my dominant in my eigenvector. So here was our eigenvector. Its components were 1.12 and 1. And so if I come back here and I look at this, you can see this is 1.12. So the ratio of our components of our transformed vector after 15 multiplications by a pretty much is already pointing in the direction of the dominant eigenvector. And so the conclusion that we want to draw is, in the long run, at what rate is the population growing, and explain what the expected number of infants and adults will be per 100 adults. Will the elf population become overpopulated? So let's see what happens here. We've said that as t approaches infinity, this equation, this vector equation that we wrote up here, which is this guy, we're making the argument that as t approaches infinity, again, the second set of terms, this is essentially negligible, this whole thing, because that's going to revolve around taking a smaller base to a large power, and comparatively, this term right here is going to be dominant. And so this is going to be negligible. And so what this means that as t becomes really large, the ratio of infants to adults will be 1.12 to 1, which is, that's our eigenvector right there of our dominant eigenvalue. And each time you increase t by 1, you'll just get one more factor of 1.79. So here's what we can say. We could say that as t approaches infinity, the population will continue growing by 79% over each 5-year period. We don't want to say each year because every value increment of t represents a 5-year period. The ratio of infants to adults will be 1.12 to 1. So that ratio, no matter how much I continue to scale these two components, as long as they're scaled by the same factor, which they are, they're scaled by this coefficient here, the ratio will always be 1.12 over 1. So that's for one adult, there'll be 1.12 infants. So if I scale this up by 100 and scale the infants up by 100, that translates to, for 100 adults, this ratio is 112 infants to 100 adults. Now that's a perfect long-run analysis. Now, as you're probably noticing, it's really not entirely necessary, unless you want to graph the populations over time, to calculate these values of k1 and k2. This value isn't so much important as is which of these two vector equation terms is dominant. And we can basically just look at the eigenvalue and tell that right away. In fact, if we wanted to really make this problem short, we just had to look at the largest lambda and the corresponding eigenvector. And this will tell me that as t approaches infinity, the vector will grow by this factor, and the ratio of the two populations will be 1.12 to 1. So we're doing extra work, but we're performing some mathematics to be able to see it. However, it really just suffices to look at the lambda and the v corresponding to that dominant eigenvalue.